So today we're going to solve a problem that it's a little bit more difficult than the standard problem. There's a couple of things on here that make it a little bit more difficult. One of them are some of the units that we're going to have to deal with, including miles per hour. And then another one is that we're going to kind of convert our efficiency equation that we typically use for these pump problems into a power ratio as opposed to an energy ratio. So that's kind of where we're going with this problem. All right, so let's get into it. Dr. Corbett is an avid alligator hunter. Before skinning the gators that she harvests, she hoses them off. And she has figured out that she needs a velocity of 31 miles per hour of this fluid stream in order to clean the hide. She has a pump that draws 5 amps at 120 volts. She also thinks she's going to be using the nozzle at a height of 12.5 feet above the surface of the water where she's pulling the water from down there at the bottom. She also expects that she's going to get an efficiency of 38% based on the owner's manual that she has for her pump setup. And so the question here asks, what diameter of nozzle should Dr. Corbett use in order to make all of this work? All right, so what we're going to do is we're going to go up here and look at some of our equations that we have to use with respect to pumps. And if you look right here, you'll notice this is kind of our basic efficiency equation that we will typically use in most cases. This is the one that I'm going to use in this case as well. So here's how it goes. It basically says that your efficiency is going to be equal to 1/2 of mass times the velocity squared plus the amount of weight that we had for the water times how high we had to lift the water. All of this divided by the amount of energy that we have to put into the system, which, if you're doing that electrically, is just V times I times T. All right, what I want us to not lose track of here is that with this equation, what we're essentially doing, and I want to kind of write this over to the side, this is a useful energy out divided by a required energy input. Okay. Well, one of the things that's cool about this equation is you can also set this equation up to be true where instead of having energy here, we actually think of it as power. So useful power out divided by the required power in. And I want to show you that it doesn't take that much for us to kind of modify this equation in order to make this a useful power out over required power in. And I'll show you why this is important for a problem like this. Okay, so again, we look at our efficiency, and what we can do is actually divide both numerator and denominator by T. When we see that we have there is 1/2, okay, M over T. I'm going to actually put that division by T with my M times the velocity squared plus, here I'll put this as W over T times H. Okay. And because I'm dividing both numerator and denominator by time, T, I can, in the denominator, essentially it just eliminates that T. Okay, and you see here in the denominator, this is power. In the numerator, we have also created, with both of our terms, a value that is going to be with respect to power. I want to do one last thing here as well, because I have mass in one of my terms and then I have weight in my other term based on the equation that was given up near the top. What I want to do is actually go ahead and put in here another expression for weight. Weight is simply just mass times the acceleration of gravity, and since we're on the Earth, we know what that value is. So what I'm going to do is put that value over here with G, and up here I'm going to put M. Well, this is kind of interesting because now I have a ratio of M over T and another ratio of M over T. That M over T has a name, and we can actually refer to that M over T as a mass flow rate. All right, so I'm going to write that off to the side. M over T is mass flow rate. Okay, and further, I can actually even give this a variable. We frequently will use the variable m with a dot over the top of it to talk about a mass flow rate. You're going to eventually learn that a dot like this is a time derivative, so it's basically telling you a rate of flow of mass. That's not important for now, just it's nice for us to have a different variable to use here. So I'll use m with a dot over the top of it to talk about mass flow rate. Okay, well, so let me actually replace those two terms right there with a mass flow rate. Okay, m dot. Well, this is the reason this is kind of interesting is if you look at the values that we know based on the givens in the problem. We know how efficient it's supposed to be, right? So we actually already know the efficiency value over here because it's given in the problem. We also know the velocity, right? So this velocity value right here was given right here, right? The g value that we have here is just acceleration due to gravity, so we already know that. H, which is this value right here, comes from how high she is when she is spraying this water, and that's given right here. Okay. Other things that we already know, we have voltage, which is given right here, and we have another variable here that is current, which is given right here. Okay, and so what we notice here is that we have everything. As long as we group the m over t into this mass flow rate, we have everything but mass flow rate. And I can just go ahead and solve directly for a mass flow rate, which is what I'm planning on doing. There's only one thing that kind of stands in our way here, and that is this unit of 31 miles per hour. That's going to be a pain for us to try to convert while we're in the middle of the rest of this equation. And so what I'm going to do is go ahead and convert that 31 miles per hour into SI units just right at the very beginning so that we can plug them in there and they don't make a big mess. So let me do that. 31 miles per hour. Okay. Now, probably for most people, if they haven't done a lot of work this way, that miles is probably going to be the trickiest thing for them to deal with. Fortunately, you might notice that you may have seen up here when we were up here a minute ago, we do have a value for what a mile is, and we can convert it into something that may be a little bit more familiar to us. While we're here, I'll go ahead and note that we also, this one most people know, foot is 12 inches. Most people know this one as well, but if you don't, it is right here in the reference material. An inch is 2.54 centimeters. So we'll use those in order to turn this miles per hour into something that's a little bit easier for us to deal with. First, dealing with miles. So 5,280 feet is how much distance a mile is. Okay, so that takes us into feet. We also know that 12 inches is how much length is in a foot. Okay, so now we're in inches. We're trying to go to SI though, and so what we'll do next is use our conversion to go to centimeters. So we know that we have 2.54 centimeters in an inch. Okay, so far so good there. And you know, now if you're kind of thinking about this, we're in centimeters per hour. If we kind of go through and go ahead and cancel a few things out here, what we're left with right now is centimeters per hour. This might be better if we had this in something like meters per second. So let's go ahead and convert the centimeters into meters. Okay, there's 100 centimeters. There are 100 centimeters in a meter. Okay, lastly, that gives us now meters per hour. We probably want to convert the hours to seconds. Okay, and there are 3,600 seconds in an hour. Okay. So now, after having converted all of these items, we can, or kind of setting it up at least, we can go ahead and punch in the variables. So 31 times 5,280 times 12 times 2.54. Okay, so far so good there. Now we're going to divide by 100 times 3,600. All right, and so the number of meters per second, because if you actually think about knocking the rest of these units out of here, the centimeters cancel centimeters, and the hour cancels hours, and we're just left with meters per second. And the number of meter per second is 13.858. Okay. And the reason that I wanted that is so that I can actually use the equation that I highlighted up here, where I kind of found all the variables in there. I want to use that and make it a little bit less cluttered. So 38%. The best way in my mind to do these efficiency equations is just go ahead and mentally convert your percentages into decimals. It makes them easier to deal with, and you don't have to multiply by 100% at any point. So that's what I will do there. 38% is equal to 0.38. We're going to set this equal to 1/2 m dot. So that is actually what we're going to try to solve for. So I don't need to plug anything in for that just yet. Here I'm going to put in 13.858 meter per second. Okay, that's going to be squared. Okay. To this I'm going to add again that mass flow rate m dot times gravity, 9.81 meter per second squared. Okay, and then multiply that by the height that I have, which is 12.5 feet. Okay, now that's going to make us a little bit of an issue there, because feet is not the same length unit as we've been using in our other aspects of the equation, and so I'm going to go ahead and do a little bit of conversion here as well. A foot is 12 inches. A centimeter is 2.54, or it's, excuse me, 2.54 centimeters is an inch. Okay, and then lastly, I'm trying to get this into meters, and so there are 100 centimeters in a meter. All right, so that is everything that I need in my numerator. Here's what I've got in my denominator. Okay, in the denominator I have 120 volts, and I have 5 amps. Okay. Now, units are always important in these equations, and so it's worthwhile to spend a couple of seconds here making sure that we have our units properly done. So let's actually just do that numerator denominator. We better have the same units in the numerator as we do in the denominator. So let's say down here I take volts times amps. That means denominator is going to be watts. Awesome. That's actually a really good thing. Okay, up here, let's assume we have something for this mass flow rate. Okay, a mass flow rate is how quick mass flows, all right? So it would be in mass per time. Our common unit that we use for mass is kilograms, and a common unit we use for time is seconds. So let's just say this m dot would be in kilograms per second. Okay, so what that ends up giving us is kilograms per second times, here we've got meters per second, but that's squared, which gives us meters squared over seconds squared. Okay, and what this whole thing gives us is kilogram meter squared per second cubed. All right, Well, I want to show you this is we can actually say kilogram meters per second squared. Okay, so what if I actually did this? I said, let's take this kilogram and put it over here, kilogram, along with one of those meters, okay, per second, so it's per second squared, all right? And then we actually would then have a meter over here, okay? What I want to show you there is that what I have set up in this fraction right here, this is the definition of a Newton, all right? And if you think about that Newton times a meter, all right, I'll do that in a different color. A Newton times a meter is a joule. All right, so now we have joules per second, which that means that whole thing is just going to be equal to a watt. Okay, and I'll do that with a slightly different color here. Okay, so my point with all this, I know I'm kind of belaboring it, but this whole thing is a watt. And I've kind of shown that by looking at all the units, assuming that m dot is in kilograms per second. Okay, good there. We have watts over watts. That's good because it ends up unitless. Now down here, let's actually cancel some of these units out. We've got feet canceling feet, inches canceling inches, centimeters canceling centimeters. And what we end up with here for everything to the right of m dot is that we've got meters times meters. All right, and then we have seconds squared down here. So what this ends up giving us is a kilogram per second for my m dot times meters squared per second squared. You can see that's exactly what we had over on the left side before we started manipulating it, and so I'm going to use the exact same logic and say this is all equal to a watt as well. So we've handled the units. And what that means is that when we solve all of this, we can assume that the answer is going to come out for m dot in kilograms per second, like we showed just a second ago. Okay, so the next thing I want to show you is this is a pretty sweet calculator that can do this solution for you without you having to do things like factor. So let's go ahead and put in 0.38. There's an equal sign built into this calculator. That allows you to set up an equation that it will solve. Okay. Up in the numerator, let me put in a 1/2 times, okay, I can't put in an m dot, but I can put in an x, right, for my variable that I'm trying to solve for. Okay, next I've got 13.858, okay, as my velocity, and that will be squared. To this I'm going to add, again, my variable I'm using is x for m dot, so I'm going to put in an x right here, times 9.81, okay, as my acceleration due to gravity, times 12.5, times 12, times 2.54, times, or let's say divided by 100. Okay. And that takes care of all of those units over there. In the denominator, I have 120 volts times 5 amps, and that, again, is watts. All right, there's my whole expression. Once I've got it set up like this, I can hit Shift Solve, and what it does now is it shows you this variable. Gets into the weeds here a little bit, but inside of the calculator, it uses a technique where it takes a guess for the answer and uses that guess to check how close it was to find a new guess that's better, and it does that over and over again until it finds the answer. For us, we can pick anything for a problem like this, and you know, someday you'll probably study why, but there's a reason why we can pick anything for a problem like this and it'll still converge to the correct answer. All right, so it says solve for x. If that's what I want to do with this as my initial guess, I just hit equals, and it comes up with an m dot term, which is 1.709, and again, that's in kilograms per second. Okay, m dot again is a mass flow rate, 1.709 kilograms per second. All right, but that's not actually what we were supposed to find. All we've really done now is we've figured out how much rate of flow of mass there is. what I want to show you here is that the mass flow rate is related to the volumetric flow rate, and volumetric flow rate is related to the velocity that the water comes out, and that velocity is in turn related to the area of the orifice, and that area is related to the diameter. So there's all of these equations are actually encapsulated up here, and mostly what I want us to look at is this one right here, where we have the volumetric flow rate is equal to velocity times area. Okay. In order for us to use this, all I need to do is be able to convert my mass flow rate into a volumetric flow rate. And the only thing I need to do that is to just apply information regarding the density of this material. Okay. So I guess I'll kind of just assert this, is that Q, which is a volumetric flow rate, is just going to be equal to the mass flow rate, 1.709 kilogram per second. Okay, and think about what the units are of density. It's going to be a certain number of kilograms per cubic meter, let's say. And for water, we have that up here. Density of water, 1,000 kilograms per cubic meter. Okay. So what I want to do is actually use that in reverse and say, here I've got 1.709 kilograms per second. I'm going to multiply this by 1,000 kilograms in the denominator and 1 cubic meter in the numerator. What you see happens there is that kilograms cancels, and we just end up with cubic meters per second. Okay, so I can go ahead and plug this in if I would like, but it ends up just telling you, dividing this by 1,000. Okay, by the way, it has this value stored in x, so if I want, I can go in here and say x over 1,000, and that'll give that to me. So 1.709 times 10 to the minus third, and that is going to be in cubic meters. And again, per second, right? Because this is a flow rate, not just an amount of material. All right, well that's neat, because now that I've got Q, I should be able to plug this in for the equation we had a minute ago, where Q was equal to V times A, where V is velocity and A is area. Okay. And so what this tells me is that I've got 1.709 times 10 to the minus third meters cubed per second is going to be equal to the velocity. I found that a minute ago, 13.858. And that's in meters per second. Okay, times the area. And the area is something that we can express in terms of nozzle diameter, because what we're talking about there is the area through which the fluid flows. And so that just ends up being pi times that nozzle diameter squared over 4. Okay, so that's pretty much it. I take this and I solve it for D. Again, I can do that in the calculator if that's something that helps me. This value right here, neat thing is you can actually take whatever your answer was, right, and plug that in. We're going to say that's equal to 13.858 times pi times this variable x, we're going to try to solve for. Okay, I'm using x instead of d, divided by 4. Okay, again, I hit shift and solve. X, the guess doesn't matter again, and so I hit equals, and it's going to come up with a nozzle diameter. Okay, now this nozzle diameter it comes up with is going to be in certain units. Okay, think about the units that are built into this thing. It's probably going to come out in meters, right? So I'm going to say this nozzle diameter is where was that again? 0.01253 meters. But you may notice up here, all the answers were given as numbers of inches. So I don't want to leave it in meters. I want to convert this to inches. Okay, So I plug in, instead of this, I think of multiplying it by, you know, I guess what I'll do is first get it into centimeters. So there's 100 centimeters per meter. And then, so that takes me to centimeters. Then there's 2.54 centimeters per inch. Like this. Okay? So if I take x and I multiply it by 100 and I divide it by 2.54, that's going to give me the number of inches that I have for the nozzle diameter. So 0.493. inches. Okay, hopefully that answer is in the answer choices. 0.493 H. All right. So I hope this problem, seeing how to work a problem like this, a little bit more difficult one, has been useful. And if it has, I'd appreciate it if you'd subscribe to my channel. And I'll see you on the next one.